Welcome to solverfy.
So in this problem, we are given two parts here. In the first part, we are given this compound ethyl butyrate, which contains carbon, hydrogen, and oxygen. And we are said that the combustion of 2.7 milligram of this ethyl butyrate produces 6.32 milligram of carbon dioxide and 2.58 milligram of hydrogen. We have to find out the empirical formula of the compound. All right. So um, before we solve this problem, let's look at the steps we will follow to solve it. So the first step here will be we'll find the number of moles of CO2 and H2O which is produced from the combustion. And from the number of moles of CO2 and H2O, we will find the number of moles of carbon and hydrogen. So we'll find the number of moles of carbon in CO2, and we'll find the number of moles of H and H2O, and from this number of moles we'll find their masses. That means the mass of carbon and the mass of hydrogen in CO2 which is produced. And since the ethyl butyrate is combusted to produce only carbon dioxide and water, that means the mass of carbon and hydrogen we will calculate from this number of moles of CO2 and H2O, that is the mass of carbon and hydrogen in ethyl butyrate. So that way we can find the mass of carbon and hydrogen in the original sample or ethyl butyrate. Then we will convert those masses in ethyl butyrate or those masses of carbon and hydrogen in ethyl butyrate into their number of moles. And then we will divide each number of moles by the smallest number of moles to get the simplest whole number ratio of moles. And in this case, in the step 3, what we'll do is here not only carbon and hydrogen, we will include, since we have oxygen here also, since we are producing oxygen, so we are given the total mass of the ethyl butyrate. So we'll subtract the mass of carbon and hydrogen from the mass of ethyl butyrate to get the mass of oxygen. In this way, we will know the mass of carbon, hydrogen, and oxygen, and then um, we'll find their um, number of moles, and then we will divide each number of moles by the smallest number of moles to get the simplest ratio or simplest whole number ratio of the moles. And from the simplest whole number ratio, we can find or determine the empirical formula of the ethyl butyrate. So let's start with our step 1 here. So step 1 is we'll have to find out the number of moles of carbon dioxide and H2O produced. So we just do it, we just divide the mass of CO2 produced by its molar mass. Mass over molar mass will give us the number of moles of CO2 produced. And same way for the number of moles of H2O, we divide the mass of H2O produced by its molar mass to get this number of moles. Now in step 2, we will find the number of moles of carbon and hydrogen in those number of moles of CO2 and H2O. So since in we can see that in one molecule of CO2 we have only one atom of C. That means 1 mole of CO2 will produce 1 mole of carbon. That means the number of moles of CO2 is also the number of moles of carbon. Now, from this number of moles of carbon, we can find the mass of carbon which is produced. That simply we just multiply this number of moles by the molar mass of carbon, since we know that number of moles is equal to mass over molar mass. That means mass is equal to number of moles times molar mass. And this is the mass of carbon which is produced in CO2. And in the same way, we will find the number of moles of H in H2O. And since in one molecule of H2O, we can see we have two H or two hydrogen atoms. That means in 1 mole of H2O we will have 2 mole of hydrogen. That means we will multiply the number of moles of H2O by 2 to get the number of moles of hydrogen. Now this is our number of moles of hydrogen, and from here we will find the mass of hydrogen in water, or mass of hydrogen produced. So as same way, we just multiply this number of moles of hydrogen by the molar mass of hydrogen to get the mass of hydrogen produced. So now we know the number of the mass of carbon and mass of hydrogen produced, and these are also our mass of carbon and hydrogen in the ethyl butyrate. Since ethyl butyrate is completely combusted to produce carbon dioxide and hydrogen and water, that means the mass of carbon and hydrogen we are getting here are the mass of carbon and hydrogen in our ethyl butyrate. So now will determine the mass of carbon and hydrogen as we got in the mass of carbon and hydrogen in the products. So these are our mass of hydrogen and carbon in ethyl butyrate also, and then we will determine the mass of oxygen ethyl butyrate by subtracting the mass of carbon and hydrogen from the mass of ethyl butyrate to get the mass of oxygen in ethyl butyrate. Now we know the mass of carbon, we know mass of hydrogen, we know mass of oxygen, and now we will find out the number of moles of each of these. So here is how we find the number of moles. We just divide each mass by their molar mass. So for carbon, the molar mass is 12.01. We divide the mass of carbon by its molar mass to get this mole, and same way we find out the number of moles of hydrogen and oxygen. And then in the next step we will divide each number of moles by the smallest number of moles, and here you can see that the smallest number of moles is this one. That means we divide each number of moles by the smallest number of moles to get a mole ratio. And here is our mole ratio. So here you can see that for carbon the ratio is 3, for hydrogen it was 5.97, which is close to 6, and we will just assume it as 6, and for oxygen it's 1. That means the ratio here is, for CHO the ratio is 361. That means um so from the ratio we can find out the empirical formula, and we can write it C3H6O. Since our ratio is 361, we'll just write C3H6O as our empirical formula. So this is the empirical formula of ethyl butyrate. Now I move to our next problem. In the second problem, we are given a sample of nicotine, which is a component of tobacco and is composed of carbon, hydrogen, and nitrogen. And we are given a specific massive sample of nicotine combusted, producing carbon dioxide and hydrogen, water. And we have to find out the empirical formula of nicotine. So that's the same procedure as the previous problem, but in this case we have a little extension where we're given the molar mass of the nicotine, and we have to find out the molecular formula. So let's start finding out the empirical formula of nicotine first, following the previous procedure. So first what we do is we find out the number of moles of CO2 and H2O as before. We just divide the mass of CO2 and H2O by their molar masses to get the number of moles of CO2 and H2O. And then again we find out the number of moles of carbon in CO2, which is same number of moles of CO2, as one molecule of CO2 contains one atom of carbon. That means the number of moles of CO2 is same as number of C. And from the number of moles of C, we find the mass of C in CO2. We just multiply this number of moles by the molar mass of carbon to get the mass of carbon produced. Same way we find the number of moles of hydrogen in H2O. And since in one H2O we have 2H, that means 1 mole of H2O will produce 2 mole of um, H, and that means this mole of H2O will produce 2 times this mole of hydrogen gas, and this is the number of moles of hydrogen produced. and we just multiply this by the molar mass of hydrogen to get the mass of hydrogen produced. Now we know the mass of carbon and hydrogen produced, and from here we'll find the mass of nitrogen. So since the nicotine is being combusted to produce CO2 and H2O only, that means the mass of carbon and hydrogen in CO2 and H2O is also the mass of carbon and hydrogen in nicotine. So we assume these masses and carbon and hydrogen in nicotine, and then we subtract these masses from the mass of nicotine to get the mass of nitrogen. Now we know the mass of nitrogen. We know the now we know the mass of carbon, hydrogen, and nitrogen. And what we'll do is we will find out the number of moles of each element just by dividing each mass by their molar masses. So we divide each mass by their molar masses to get the number of moles of carbon, hydrogen, and nitrogen. And then we move to our next step where we divide each number of moles by the smallest number of moles to get the simplest ratio. So the simplest whole number ratio. So we divide each number of moles by the smallest one, and we get for carbon the ratio is 5, for hydrogen it's 7, and for nitrogen it's 1. So the simplest whole number ratio here is 571. And from here we can easily find out the empirical formula of nicotine. And here is our empirical formula, which is C5H7N. Since we had 5 carbon, 7 hydrogen, and 1 nitrogen in the simplest whole number ratio, that's why this is the empirical formula of the nicotine. Now from here we can find out the molecular formula of nicotine, which is simply we put an N over this empirical formula, where N is the molar mass or molecular weight of nicotine over its empirical formula weight. And N should be, and N must be, a whole number multiple. That means if we get a fraction of N, we will consider the nearest whole number as the value of N. So we are given the molar mass or the molecular weight of nicotine. We have to find out the empirical formula weight of nicotine to get the value of N. And that's very simple how to find the empirical formula weight. What we do is we simply add the atomic weight of uh, each atom present. So we have carbon here, and carbon's atomic weight is 12.01, and we have 5 carbon. That means we multiply this by 5. Then we have 7 hydrogen, and we multiply the hydrogen's atomic weight by 7. And then we have nitrogen. So this will not be AMU, it is gram per mole, since all the values are given in. So since you're given the molar mass of nicotine, we'll have to consider the molar mass of each uh, atom present. And if we are given the molecular weight of nicotine, in that case we had to consider the atomic mass unit of each atom present. Okay, so that way we find out the molar mass of the empirical formula, or we find out the empirical formula weight. Now we know the empirical formula weight, and we will simply divide the molar mass of nicotine, which is 160, and we're given 160 plus minus 5. We just ignore those plus minus 5 because that will not give us that much difference in values. We just consider it 160 gram per mole as the nicotine's molar mass, and we divide that by the empirical formula mass of nicotine, and it will give us 1.97, which is close to 2. So our molecular formula will be we'll just um, replace the value of ns2 and that means we multiply each of these by 2. Now we have C10 H14 N2, and this is the molecular formula of nicotine.